Now we're going to go into more detail regarding Hess's law. Hess's law, as you may recall, holds that the delta H of a reaction, the change in enthalpy of a reaction, is the same regardless of whether the reaction occurs in a single step or in multiple steps. Let me show you an example. Let's take this reaction where monoatomic sulfur gas reacts with 1.5 molecules of oxygen gas to make 1 molecule of sulfur trioxide. The change in enthalpy associated with that reaction is negative 395 kilojoules. All right, so nice exothermic reaction. Alternatively, we could look at two separate reactions. The first, where monoatomic sulfur reacts with oxygen gas to make sulfur dioxide, and the second, where that sulfur dioxide then reacts with half a molecule of oxygen to make sulfur trioxide. So if we look at those two reactions and add them together, we can cancel out species that are the same on opposite sides of the reaction. So the sulfur dioxide molecule, being a reactant in one and a product in the other, can cancel out. And then we're left with the sulfur gas, the diatomic oxygen plus a half a diatomic oxygen, 1 plus a half equals 1.5 oxygens. And those two reactants combining together give me 1 sulfur trioxide. So that is a two-step process that accomplishes the same as our initial reaction. Now, if we add the two reactions together, we can also figure out the total delta H of the process by adding the two individual delta H's together. So negative 296 plus negative 99 gives me negative 395 kilojoules. So you can see that the delta H has the same value regardless of whether the reaction occurs in a single step, as up here, or in two steps, as down here, 1, 2. So this is really a function of the fact that delta H is a state function. All we care about is the difference between the final state and the initial state. The number of steps we take to get from the final state to the initial state does not matter. Okay, so we could do this in one step, or we could do it in 50 steps. The delta H should be the same for the change. Let's do another Hess's law example. Calculate delta H for this reaction. Nitrogen monoxide plus singlet oxygen gives nitrogen dioxide. Okay, we want to calculate delta H for that reaction given the following information. So we're given two reactions. In the first reaction, we have two ozones, O3, break apart into 3 O2 molecules, and that has a delta H of negative 427 kilojoules. In the second reaction, we have oxygen splitting apart into two oxygen atoms, and that requires an energy input of 495 kilojoules. Okay, so given all of that information, can we calculate delta H for this desired reaction here? Oops, we have one more given, sorry. Nitrogen monoxide plus ozone react together to give nitrogen dioxide plus oxygen, and the delta H for that is minus 199 kilojoules. All right, so we're probably going to need all three of these reactions to get the desired reaction. Now, what you have to do is look at your desired reaction. Okay, that's this reaction up here. And then manipulate the given reactions to end up with the reaction that you desire. So I'm going to kind of color code this. I have my nitrogen dioxide present up here, and the only place where I see it in the given reactions is down here. And I have the same number of moles of it, just one, and it's on the product side. So I'm going to assume that I need to kind of keep this last reaction in the direction that it's going. The singlet oxygen I have here And I can see that I'm probably going to need to divide that reaction by 2, and I'm also going to need to flip it over because over here, oxygen is on the reactant side. Here, it's on the product side. So I'm going to need to flip it over so that it's going to be on the reactant side. Finally, I have nitrogen monoxide, and the only place I see it is down here. So I'm going to I have the right number of moles of it, and I can probably lead that reaction in the direction that it is. So I'm going to rewrite the reactions down. Now, this last reaction, I determined that I don't need to change the stoichiometric coefficients, nor do I need to change its direction. So I'm just going to recopy it as written with its delta H unchanged, minus 199. This reaction, the middle reaction, however, this reaction right here, that reaction I'm going to need to flip over because I want to have the singlet oxygen as a reactant. And not only do I need to flip it over, but I'm pretty sure I'm going to need to divide it by 2 because up here I only need one of these. So I want to divide their whole reaction by 2 so that I get rid of this coefficient here. And if I divide it by 2, that means I'm going to have half an oxygen. Now, here, I'm going to have to take this number and divide it by 2 and also change the sign. Because in reversing the reaction, I have to change the sign of the delta H. And in dividing the reaction by 2, I also need to divide the delta H by 2. So that's going to be minus 495 divided by 2 kilojoules. Now, I'm noticing something here. I have these extraneous species here. In the desired reaction, okay, the desired reaction that I have up here, I don't have any ozone. So I'm going to need to do something. Ozone is O3. I'm going to need to do something to get rid of this ozone here. And it's probably not a coincidence that they gave me this, this top reaction here. So can I use that to get rid of my ozone? Well, it looks like I have ozone on the left side from this reaction here. So if I take this reaction and flip it over and divide by 2, it looks like I'm going to be able to get rid of the ozone. So I'm going to divide the reaction by 2 to get 3/2 of oxygen. Oops, here, I'm listing my parentheses there. And going to 1 molecule of ozone. So I flipped the reaction over and I divided it by 2. So that means I'm going to have to flip the sign of the delta H, so it's plus 427 kilojoules, and I'm going to have to divide that by 2, so I'm putting a 2 there. Okay, so now you have to look at the reactions and see if you can cancel things that you don't want. Okay, so I'm going to draw some lines here to try to make it a little bit neater. So in adding these reactions together, I can cancel out the ozone. What's more, on the right side, I have 1 plus 1/2 is 3/2 oxygen. So that will cancel out the 3/2 of oxygen I have on the left. So now my final reaction when I add everything up is that the nitrogen monoxide plus the singlet oxygen gives me nitrogen dioxide. And I think that is it. Now, does that match up with my desired reaction? NO plus O gives me NO2. And O plus O gives me NO2. So now I can calculate the delta H by taking minus 199 kilojoules plus negative 495 divided by 2 kilojoules plus 427 divided by 2 kilojoules. And if you do all of that, the delta H comes out to be minus 233 kilojoules for this reaction. So this is the delta H of the reaction, which we determined by Hess's law. The delta H corresponds once again to this reaction right here, this final desired reaction. So the best way to do Hess's law problems is to just practice lots and lots of examples. And as you practice the examples, you can apply these general strategies. First, as I just did in this example, take the desired reaction and work backwards. Working backwards from the desired reaction is a really good strategy for solving these problems. You can use the reactants and products, just like I did, to figure out how to manipulate the other reactions. Should you reverse them? Do you need to multiply or divide by a stoichiometric coefficient? As you saw, you can reverse reactions as needed. And whenever you reverse a reaction, you have to reverse the sign of delta H. And finally, you can multiply reactions through by stoichiometric coefficients in order to get the needed number of reactants and products. So those can be whole numbers, those coefficients, or you can use fractions. Okay, so you could think of that as multiplying by a fraction or just dividing by a coefficient, for example, dividing by 2, as we just did in that example. Okay, this will help you to get the desired number of reactants and products so that you can cancel out the species that you don't want. So if you follow all of these steps and do a dozen or so Hess's law problems, you should get really good at this. And the beauty of a Hess's law problem is you can kind of tell when you've got it right.